Thank you, everybody, for sticking it out to the end, and thank you to the organizers for organizing such a wonderful meeting and for having me here. So I will start by just mentioning a couple of things that I'm not going to talk about today, but if you want to ask me about them afterwards, feel free. So one thing I'm not going to talk about today is an experiment that we have running on this little tiny island halfway between South Africa and Antarctica, looking for cosmic dawn. Why do you go to little tiny island? Well, there's no detectable RFI in the FM band, and I think we are the only radio observatory that can say that on the planet. There are unfortunately lots of mice there too, but come ask me afterwards if you want to hear about that. Another thing I'm not going to tell you about today is galaxy clusters with the Mustang 2 camera on the Green Bank telescope, which has 9 arcsecond resolution. So if you care about such things, this is an example of a pressure profile you can get. The blue points are ACT, and the red points are the pressure profile in SE you get when you combine Mustang 2 from an 11-hour observation. So you can see it's a huge step up. So I don't know, if there are some people in the audience that care about this sort of thing, you can also come to ask me afterwards. What I am going to talk today about is these things, fast radio bursts, and searching for them with HIRAX, which Mamita mentioned earlier this morning. So what are fast radio bursts? Well, we don't know. We'd like to, but we really don't have any idea. So basically, if you looked up at the sky and you had radio eyes, what you would see are bright AGNs, the usual radio sources. But then every few seconds to a minute, there'd be a flash that went off. And these flashes would last for 1,000th of a second, but during that 1,000th of a second, they'd be among the brighter things in the sky. And you'd see them, there's a lot of them. So, estimated rate is thousands per day in the sky. So they were only discovered about 10 years ago. So why is that? That's because of dispersion. So if I have radio waves coming through a plasma, so going back to second-year physics, there's a plasma dispersion relation. And what that means is that high-frequency rays travel a little bit faster than low-frequency waves. So low-frequency waves get slowed down by the plasma. And so a thing that starts out as 1,000th of a second at the source, but then when it gets to us, has been not smeared out, but stretched out, and can be spread over several tenths of a second to several seconds to even minutes in some cases that I think will be seen in the near future. And so if you average the thing that lasts 1,000th of a second over seconds, you're not going to see anything. So somebody had to actually go out and look for these. Now this dispersion has been well known basically since the beginning of pulsar astronomy. But these weren't noticed because the dispersion measure, which is just the electron column density, was much higher than you can get from the Milky Way. So pulsar astronomers, quite sensibly, like the drunk, looked for their pulsars where the street light was shining. They looked at the dispersion measures that they thought you'd see in a galaxy. So when you see these flashes at much higher dispersion measure, so much higher column density than you could ever get from the Milky Way, that's not where they were generally looking because they didn't know that there was anything there to see. Now, this dispersion measure unit I think is alien to everybody but pulsar astronomers. It took me a while to get used to it. So it's just the column density of electrons, but the handy rule of thumb is you just take the dispersion measure, ignoring cosmology, there's a little bit of a redshift effect, divide by 500,000 and that gives you the optical depth of Thomson scattering, right? So, I'll see this again later. What is the dispersion measure through a rich cluster of galaxies? Joe, you can tell us, right? Yeah, so multiply by 500,000, so the dispersion measure through a rich cluster of galaxies is 5,000. So that's a handy thing to keep in mind. Now, first one was discovered for about 10 years ago. You've only really started to hear about these in the last couple of years. Well, why is that? Part of the reason that is for a long time, people didn't believe they were real. Why is that? Well, so they were discovered by Parkes telescope, and for many, many years, only Parkes had ever seen them. And Parkes saw lots of things. So these are great fast radio bursts, right? See that nice delay at low frequencies that arrives later? Well, no, these are not fast radio bursts. So if you look carefully at these things, you see that the delay is not actually, you expect from plasma dispersion, the delay should go like lambda squared. And if you fit that carefully, the delay is not quite lambda squared. Now, another reason they were pretty sure they weren't real, by real I mean external celestial sources, is that they saw them in multiple beings. Well, what does that mean? That means the telescope was out of focus. Well, if the telescope's focused at infinity and it's out of focus, that means it's happening nearby. So probably not astronomical if it's nearby. When you look in more detail, an even bigger flashing red flag is that these things were common around noon on weekdays, which is pretty clearly not astronomical. And they finally tracked this down to if you were microwaving your lunch and you opened the door while the microwave was still on, it would put out a flash that looked very much like a radio burst. But you know where the microwave oven is, and if the telescope's not pointing towards it, and it's not during lunchtime, you're pretty sure that it's actually not one of these things. So tracking this down actually helped strengthen the case that FRBs were real. But of course, eventually enough telescopes got on the case that it was, became very convincing that these are real astronomical objects. So just a brief history is that the first one was discovered. It was actually in archival data that the thing went off in 2001, but nobody looked at it for 6 years. And so it was actually noticed for the first time by Duncan Lorimer in 2007. And then sort of that one was very clear. Then like over the next several years, there was sort of a handful that were put out, but they were much lower significant, sort of like 10 or 12 sigma, which may sound like a lot of sigma, but it is actually not. The phase-space search for fast radio bursts, because of the number of time samples and the number of possible dispersions you had to search through is huge. So basically 10 sigma is the bare minimum just to get past Gaussian statistics that you might have a real event. So people weren't really sure. Maybe these are real, maybe they're not. Then Arecibo finally found one in 2014, but it was sitting right in the galactic plane. And the receiver came from the same lab as the lab that built the Parkes receiver, so people were still not totally convinced. And then 2014, they found a circularly polarized FRB at Parkes, but also they found it very quickly. So they had real-time searching up and running by then. So they, got all sorts of telescopes to go off and point and see if there wasn't any counterpart, and there wasn't. So that was very sad, but it was at least nice to see that people could get telescopes on these things quickly. So then 2015, this is actually started as a HIRAX pipeline test. The algorithms people have been using were not going to scale up to an instrument the size of HIRAX, so I wrote some code to try and do a faster search, and then Wei Li Pen was like, oh, we've got archival data we could test this on, so we ran it through, and lo and behold, it's better to be lucky than good. So we found an FRB with the Green Bank telescope archival data, and this time the receiver did not come from the same lab as the other receiver, so it's not a lab thing where somebody has a component that sparks and makes FRB type things. And also, we could do lots of fun things. I don't have time to go over them all, but we could do lots of fun things with this event. So it was the first one that had linear polarization, and from that we were able to measure Faraday rotation. It's something like 100 sigma. I forget how many, but it was a lot. And the Faraday rotation was quite a bit higher than you could explain from just the Milky Way or along the line of sight from sort of the general intergalactic medium. And so that means that there had to be some electrons, magnetized material nearby the FRB that was providing the rotation. But we could also show that it wasn't too nearby through higher order terms in the dispersion relation. And then sort of at this point, the floodgates were, one more important thing about this one is that we saw it at 800 megahertz. So this was the first one that had been seen outside of L-band. So for instruments like CHIME and HIRAX are going to be looking at lower frequencies. It was nice to know that there'd be a thing to look at, because to date there had been 0 signals seen. And people had looked at lower frequencies and not seen anything and thought maybe this meant that there weren't going to be any lower frequency bursts to look at. So then, in 2015, 2016, another one went off and somebody went off and took a radio telescope and pointed at the error box of that one and saw a fading radio source and was like, oh, that fading radio source must be the radio counterpart to the FRB. No, sadly, that just happened to be a variable AGN. So there were a lot of great papers written about this that were completely wrong, but we'll eventually be right when we do have proper counterparts. And then more telescopes turned on, so in 2016, Utmost, which is a cylinder array in Australia, began seeing things. And then 2017, 2018, ASCAP and CHIME turned on, And in 2018, CHIME announced its first few FRBs, and ASCAP announced 20-ish new ones. And then CHIME had a big dump just a few weeks ago with another 13. And so up to this point, only one FRB had ever been seen to repeat. CHIME found a second repeating FRB. Did the others repeat? They might. We don't. It's hard to get telescope time to stare at something that's not happening, so we don't have great statistics yet, but that will also change. So as of today, there are two FRBs that have been seen to repeat, and there are 65 total events at frbcat.org. So if you want to go look up all the stats on all these things, you can do that. So we've seen 65 of these, and we're really not any closer to knowing what they are. And the big reason is that, we just don't know much about them. So 2 have been seen to repeat. Do the others repeat? We don't know. So at least for some of these, at least some of the electron density, the dispersion measure must come from close to the FRB. The polarization properties are all over the map. So for the ones that have had polarization properties measured, some were strictly polarized, up to 20%, some are not. Some are linearly polarized, up to 80%, some are not. They're all over the place. The rotation measure is all over the map. So anywhere from 0 to 100, a couple hundred. I think there's actually one that's higher than 186. And then the repeater has a dispersion measure of 10 to the 5, which is a crazy high number. That only happens near massive black holes. So maybe it's around a black hole. Who knows? Spectral behavior is all over the map. I mean, you'll notice I didn't say spectral indices, and that's because the behavior is complicated enough. Even referring to it as a spectral index is not, it doesn't look like a power law. There's lumps and notches taken out. Some of this is from propagation effects. So as you have your waves moving through the noisy interstellar medium, the FRBs twinkle, just like a night star twinkles. So they twinkle from the Milky Way, and so some of the spectral behavior is coming from that. But we don't know how much of this is coming from the intrinsic bursts, whether there's anything interesting there. And the durations are all over the map. So some of them. The intrinsic duration of the events is 10 microseconds. Some of them is a few milliseconds. There may be some that are longer, but at that point it starts to look like RFI. So we really don't know very much about them. And why aren't there more? So the inferred rate I've said is thousands per sky per day. But we found a couple dozen and a few dozen now in several years. And that's just because the fields of view of the first telescopes to look at these were really small. So Parkes sees 10 to the minus 5 of the sky. So if there's a few thousand going off, so it's 1 in 70,000, so if there's a few thousand per day, Parkes sees one every few weeks, which is about what they saw. So if you want to do better in this, if you want to get more of these, you need more collecting area, because more collecting area lets you see further FRBs, fainter FRBs, and you want a lower sky coverage, right? 10 to the minus 5 of the sky is a pretty small field of view. So one thing that's doing pretty well now is ASCAP, not involved with this. So it's got 12-meter telescopes, 36 of them, and they've got 36 beam receivers. So the Parkes has got one telescope with 13 beams. ASCAP has got 36 beams. So it's got about, each of those is half of a Parkes. You put 36 together, you've got 20 times Parkes. And so even though it started in 2017, it's already found as many FRBs as Parkes. Then CHIME is just turned on. CHIME will really change the game. It's got a field of view that's, 100 square degrees, a couple hundred square degrees. So there's a large error in this, but it should see, many FRBs per day. And I expect that the rate that they report them will go way up. They're still in the early days of getting their telescope sorted out. So yeah, stay tuned for that. And the big reason the biggest single reason I think we haven't made more progress is location. So the telescopes that have found the FRB so far are low resolution. You want that because you want the large field of view. But if you don't have any, if these things don't repeat and you don't have any way of taking your low resolution image and figuring out which galaxy you came from, you can't say what the redshift is, and then if you don't have a redshift or a sort of galaxy host, then you're sort of really shooting blind. So this is where HIRAX comes in. So as Mimi just said, the main goal of HIRAX is dark energy, but it turns out to be a perfect instrument for fast radio bursts. And these are all the people that have been helping out with this. So the design is 1,000 close packed 6-meter dishes, and with several, many times the, 50 times the field of view and 9 times the collecting area of Parkes, we should have a much bigger event rate. There's still uncertainty based on where the spectral behavior, on average goes as you go to lower frequency. So we have a site, which is great. We're supposed to start construction late this year. We also have a bonus pet aardvark. We've seen its hole, so we'll have to be careful with the aardvark on site. But one of the great things about working in South Africa is that the RFI is really under control there. So that's real RFI data. Inside the HIRAX band, there used to be UHF TV stations, which the government turned off to reduce RFI for SKA. So that's great for us. So this may be, the HIRAX band may be the cleanest band at the site. So I won't say too much about the core, but a thing that HIRAX can do that's really nice is that if you build more dishes and put them a long ways away, you can now localize FRBs. We're gonna, and it doesn't take that many, so with something in order 50 or 60 dishes, you can basically get enough signal noise to localize in VLBI to a typical error of 30 milliarc seconds, more or less all the FRBs that HIRAX sees that don't repeat. So this will be really exciting. And there's a lot of support. I don't, do you know? No, that's a different guy. That's Austin, that's not Cabello. So we're gonna build outrigger stations across Southern Africa, and Perimeter is supporting some of this. But with this is what the beam looks like. So that image right there shows the beam. That image is a half arc second by a half arc second. So it'll just really change. So not only will we be able to say which galaxy they came from, but we'll be able to say, well, where within galaxies are FRBs coming from. And just to give you a little flavor, this is site testing under the shade of a baobab tree in Botswana. The site there looks pretty good, so this will be one of our regular locations. What are we going to do with these things? Well, for starters, we have to figure out what they are. But I'm a cosmologist, so I'd also like to figure out what we can learn about the universe that has nothing to do with FRBs from these, because they give us exquisite arrival time information, right? So you can time these things to better than a millisecond. And you can measure the, whenever Z-weighted electron column density, again, to, parts in many thousands or tens of thousands. So a handy rule here, which I worked out yesterday, is that to like a ridiculously high precision, like 1% or better, it turns out that if you want to convert DM to redshift, you just divide by 1,000 for the cosmological part of the DM. So if there's anything where this sort of information might be useful, you can use FRBs as probes of cosmology. So a few cases where this has been thought about. So Matt McQuinn put out a very nice paper a few years back that sort of was one of the things that kickstarted this, showing that with order 100 FRBs with positions and redshifts, you could track down missing baryons if they've been pushed out in halos, because you don't see cold electrons very easily, except FRBs tell you very clearly what they are. They pick them up very easily. So at a sort of 100 FRBs, you start to change the game on missing baryons for galaxy and group size halos. You can also do a lot of fundamental physics. So you've got really precise arrival time over a range of frequencies. So if photons are massive, also low energy moves slower than high energy. Single event, if you just eat the dispersion measure, so that looks like a dispersion. If you just eat it, you get answers already that are comparable. Well, we will as soon as we have a few of these things to the best lab measurements on the photon mass. But the behavior of this as a function of redshift will be different for the dispersion versus photon mass, and so you can break that degeneracy down the road with enough events. And so amongst the direct measurements, this will be I think, probably the best measurement of the photon mass. Similarly, if you have an FRB going off in a halo, if the gravitational redshift is a function of energy, you would expect to see, if you violate Einstein's equivalence principle, you'd expect to see now that high energy and low energy photons arrive at different times. So they're already, I think, from what I've been able to read, the best test of the equivalence principle, or will be as soon as we have a few of them. Doesn't take much. So all these things that say they've localized these, that's wrong, because that was the FRB that wasn't actually localized. But this will change. Now, of course, you can go from group scale to cluster scale. So if you have an FRB go off behind a cluster, you need a lot of these now to have the probability be high. But if the DM is 5,000 through a rich cluster, you can get few percent measurements of the integrated optical depth, independent of temperature, through a galaxy cluster. So if you combine that with SC and FRBs alone, you can get cluster temperatures integrated through the mass. And it doesn't rely on X-rays, but it does require a lot of FRBs. So if you say, why would I want 1 million? This is a good reason you'd want 1 million FRBs. So you get a few happening behind rich clusters. Now here's one that I didn't do too much of this actual work. My main role was to just like nag people until they did the actual work. But one of the big things coming up in SC surveys is KSE. And this is a major goal of coming to CMB experiments, so I won't say very much about this, I guess. But the big issue there is that there's a degeneracy between velocity and optical depth. We care about velocity because that's cosmology, and we don't like optical depth because that's just noise. But the FRBs can measure that. So Matthew Bhattacharya showed that in this paper that came out this month, that including FRB information, sort of 10,000 to 1 million FRBs, you can actually improve on KSE measurements with S4, including with 1 million, you actually beat out S4 plus redshift space distortions. So in closing, think about lensing to these things too. So just in closing, I want to say, think big, right? This is a new tool. I think we're still in the early days of figuring out what you can do with these things. So think about it. And if you come back and say, I can change the world if you give me 1 million FRBs, we know how to build, that's just money, and it's not that much money. If you think of something, don't be shy about saying, I think I can like bust cosmology wide open if you give me 1 million FRBs. So don't be shy, even though we've only found a couple dozen, because we can get to 1 million or 10 million if you want to wait long enough. So in that, I just want to say, I think it's an exciting area. Stay tuned, and thank you all for having me here.
Thank you.
Thanks. Thank you. Very nice. You mentioned earlier that the repeater, the dispersion measure, was 5,000, but for the second one, I think is like 190 or so, right? For the one by chime.
Don't remember for the second one. Basically, the story of these has been that whenever you look at two things, they don't look the same.
So the one with 5,000, why couldn't...
10 to the 5.
Oh, 10 to the 5. Yeah. All right. Yeah, I was thinking maybe I got stuck with the cluster then. So, all right. Okay. So my second question is there any prospect to, if I remember the second one, they have a confidence region on the location, and it's not that large. I think it's a fraction of a square degree. So in principle, it shouldn't be too hard to find out, especially if they are repeating.
I'm not part of Chime, but I can guarantee you that that's the sort of thing that Vicky Caspi would be all over. Right. So I'm sure they have got JVLA proposals to do exactly that. Once you know where to look, roughly. Yep. And the Chime error boxes are smaller than single dish ones. So I don't know how long we'll have to wait, but it's probably not going to be very long.
Hi, sorry. So I'm not a radio astronomer, but I think of radio dishes as very high resolution instruments. So what is the problem with localization? If the burst comes, why can't you localize?
Single dishes are not high resolution. They're very poor resolution. The high resolution only comes when you interfere the signals. And it just turns out to be very...
Like Arecibo is a huge dish. So Arecibo?
But the wavelength is really huge. So the resolution is a few arc minutes. So maybe an arc minute, which
so when you say, so when you say you have not localized, that means you know its position within few arc minutes?
You don't know the position well enough to know the host galaxy, so you can't get a redshift.
The typical resolution is of order 10 arc minutes, or
something like
so you know within 10 arc minutes where it is.
Yeah,
or
but
5. Okay, but that is
anything by that, unfortunately. Unless you go off and point, unless it goes off again, because you can point the JVLA at it, and then if it goes off again, you can see where it went. Was. But,
Do we know enough about FRBs to say whether we'll be able to get redshift or optical counterpart for these things?
I think we have no idea.
So like a lot of these things assume that we are going to be able to get redshift for these things, right?
Yeah, no, so the redshift comes, so they're probably sitting in host galaxies. So you just need a position good enough to go off and get the redshift of the host galaxy. But that doesn't, you don't need that the FRB itself has an optical counterpart, just that it's sitting in a galaxy. And of course, if they're not sitting in galaxies, that's really interesting too. That could mean that they're cosmic strings or something, which is a viable model.
Okay, if there's no more questions, let's thank John again.
Thanks very much.